Okay, let's get started. So pretty much going to wrap up the last topic, integration by parts. So we're in the end game now. Did you guys see the movie? No?
Not yet.
It was good.
What's wrong with you people? Get together. Okay. So let's start. What was the formula? Without looking at your notebooks. By parts formula.
UV minus, hold on.
What are you
I
starting
have
with
to
the
do it
right
back, I have to do it from the middle. That makes more
You
sense.
do it from the middle?
Yeah.
Okay. So UV
Minus the integral of V du. So then the other side's UdV. Integral
What?
of UdV.
The interval, yeah.
Okay. All right. As long as you remember the whole thing, that's fine. How do you choose the U?
Liate.
Use Liate. Right? You choose the U in this order. And L stands for?
Logarithms.
Inverses. Algebraic. Trig.
Exponents.
Okay. So last time we ended with an integral that I told you guys to consider for today's lecture, x to the fifth, e to the x. Did anyone actually try to do that?
I was thinking about it, but I literally just couldn't figure it out.
Let's do something a little bit easier, and we'll do a couple more examples before I actually deal with this one, just to kind of introduce the new method that I want to talk about. Let's do something like that, and then you'll kind of see what this would require. So how would you do something like that?
U would be x squared.
Okay. So again, doesn't have a basic rule, substitution is not going to work, and so we think integration by parts, Liate, and we have an exponential and an algebraic expression. So set U equals x squared, your du would be e to the x dx, so your du would be 2x dx, and your d would be e to the x. And so this guy becomes what? So what do we end up with here?
X squared times e to the x minus the integral of e to the x 2x dx.
Right, times 2x. Yeah. So 2x e to the x dx. Okay. So as long as we can do this integral, we can find that integral. So how do we do this integral? Well, we can factor the 2 outside. So it doesn't matter. How do you integrate x e to the x?
By parts again?
I mean, we did it last time.
Yeah, we did it last time.
Yeah, but how did we do it?
Same.
It's going to be by parts again. Okay, so here we're going to choose u to be, again, the algebraic expression. Our dv would be to e to the x dx. Our du would, of course, be dx. And our v would be e to the x. And so ultimately now we get, so we have x squared e to the x minus 2 parentheses. And now we're going to do integration by parts here. So that's u times v minus the integral of v du. So ultimately we know the integral of e to the x is e to the x plus c. So this is x squared e to the x minus 2x e to the x plus 2 e to the x plus c. Now that we did that, what do you think we'd have to do for this guy?
Just keep doing that.
Keep doing that 5 times in a row. Obviously, this can be quite annoying. I'm going to tell you how to make it a lot less annoying eventually. But before that, let's do another kind of issue that can happen. So integration by parts, pretty cool. It's the way that we reverse the product rule. However, as you can see, using this formula can be cumbersome, especially if you don't have to get really complicated of a function to make it cumbersome actually. But there are functions where it can kind of be cumbersome. Before I show you how to make it less cumbersome, let's look at another particular issue. So one issue with integration by parts is sometimes it can be annoying. You have to use it over and over. Then you have all these nested parentheses. And then there's a negative sign in the formula so that it changes all the signs, and it can get pretty annoying. Let's look at this example. How would you do that one?
Cosineers?
Okay. So again, basic rule doesn't work, substitution is not going to work, so we're going to think integration by parts. We have a product here, we have an exponential function, we have a trig function. It almost doesn't matter who you pick here, but let's actually follow Liate, and the u gets to be the cosine. Our dv is the e to the x. Derivative of cosine of x?
U sine?
U sine x. Integral of that is e to the x. So we would have this guy equals u times v minus the integral of v du. This would become plus how do we continue?
Do it again?
Do it again. Okay, let's actually do it again. So we have u equals the sine, dv equals the e to the x dx. Our du would be positive cosine. Our v would be e to the x. Let's plug in the formula again. So here we had e to the x cosine of x plus parentheses. Now we're going to do integration by parts here. U times v minus the integral of v times d. Well, there's a plus sign here, so we don't really need the parentheses, but okay. Now what?
We're just gonna keep,
Do it again.
it's not gonna get you anywhere though. I don't
It's not going to get you anywhere. You can kind of see it, right? We kind of end up, wait, isn't that where we started? Like, what do we do now? The method just doesn't work now. Give up. Ideas? What do you notice about this guy?
Same as what we're starting.
It's the same as the one we started with. In fact, this guy here, you would notice, is actually the same as this guy here. What do we want to solve for again? We wanted this guy, right? So, given this equation, do you think you could figure out how to get to that guy? Do you have an idea?
Can you just like combine like terms?
Combine, like, it's algebra at this point. There's no calculus actually required. It's kind of like if you had x equals a minus x. We want to solve for x. What do? Bring all the x's to one side. So this is a kind of revolving integration by parts. This is something that can happen ever so often. That's not a technical term, by the way. I just call it that. Revolving. I don't know why I choose that term. But sometimes you're applying integration by parts, and eventually you'll end up with kind of the thing you started with. And usually this happens whenever you have functions where their integrals and their derivatives become the same after a while. And if you end up in that situation, at some point, when you get the original integral back, you just stop and solve for it just like you would in an algebraic equation. So the thing is, I can add this to both sides. Now we get two of those guys over here. And then I could just divide by 2. Of course, you know there should be a plus c at the end of any integration, the arbitrary constant of integration. So this is also something. One thing that's common, I mean, I didn't do it here. Sometimes you'll see people do something like, when they anticipate something like this is going to happen, they'll start out by set I equals to the original integral we want to compute. And then eventually they'll get to a point where they see that I is equal to e to the x cosine x plus e to the x sine x minus I. And then at that point it's kind of clear that that's the variable you should be solving for. You don't have to write that out, but it's very common for people to express it that way. So I think we pretty much covered all the issues that can come up with integration by parts. So we've seen that, yeah, some problems are straightforward, like xe to the x. Apply the formula one time and you get to the answer. Some require a substitution while doing integration by parts. So we did the integral of sine inverse of x, that kind of happened, which also brought in the other concept of choosing one as your u. Sometimes you can have to do integration by parts over and over and over again. And sometimes you do integration by parts and it revolves on itself. You get the original back. And at least, hopefully by now in theory, you know how you deal with all those situations. But I actually want to give you another technique. Well, it's not another technique, it's a refinement of integration by parts. That some people like more than thinking about the formula. And it's called tabular integration. So pretty much we want to take the process of integration by parts and we want to streamline it. Get to answers easier and figure out a way to deal with all these situations that I just actually brought up. Here's how it works. It's pretty much algorithmic. So you have an integral, and I'm going to write it in, just going to use some random notation. So let's say we have a function, say f of x, and we have another function, g of x dx. Okay? And I'm specifically thinking of my f as the u, and my g of x as the dv. So we know how integration by parts would actually work. You want to differentiate the u, you want to integrate the dv. So here's how you can actually do this a little bit more generally. You set up a table pretty much. And the u, you would keep differentiating it. So that's the first derivative, then the second derivative, then dot, 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 all the way down to the nth derivative. And I'll tell you what n represents here. How do you know when to stop this process? And the dv is the part that you integrate, right? And because you're doing Leate, these guys will be always be chosen in the same way. So suppose that is the first integral. Integrate a second time. Dot, dot, dot. So here I went through n integrals of that function. So you'll actually do this process n times. I'll tell you specifically how to know what n has to be. But once you do that process, there's now a way to actually get to the actual answer. Maybe I should use a different color here. You're going to be multiplying across diagonals, right? The astute among you would notice that I multiplied u by v, right? Because if you take dv, you integrate once, that's the v. So I'm actually multiplying by u by v. So you're going to multiply across the diagonal. And you're actually going to repeat this process all the way down. When you get to the end, you're going to multiply it across that way. So that's the first thing. We're going to find the sum of all these products. However, because the integration by parts formula has a minus sign, every time you open parentheses, the minus sign will distribute and change all the signs in the middle. So there is going to be an alternating sign thing that happens here. So it's plus on the first one, but by the time you get to the second one, it becomes negative. By the time you get to the third one, it becomes positive, etc. And it's going to be plus or minus here. And so here's how you actually finish the algorithm. We're going to take all these products and we're going to add them together according to these signs. So equals f of x times g1 minus f prime times g2 plus dot dot dot. We'll get to the n minus first term, so we get f to the n minus 1 of x times gn. All right, so that's this orange line right here. This will be a plus or minus, depending on how long you have to run this process for. And when you go back this way, it's actually an integral. So this is going to be plus or minus the integral. And that's the guy that ends that process. Now, how do we know what n is? Meaning, how long do you have to run this algorithm? We stop this process when one of three things is achieved. And it will depend on the situation. One, your derivative of the f becomes 0. There'll be a point, sometimes your function, eventually if you keep differentiating, you hit 0. This will happen for any polynomial, for example, right? So eventually if I have, say, x to the 5th, it will become 5x to the 4th, blah, 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 blah. Eventually when I differentiate it, I'll get 0 as a result. And once I hit 0, I would stop, right? And that's where the table ends. Another thing that can happen is fn times gn is the original integral. So you stop the table as soon as you realize when you look at these things beside each other, it looks like the original integral. That's like the revolving one. And you would stop the table at that point. Or 3, this is kind of the other situation. Fn gn is an integral you can deal with easier. right? So you might get to an integral where you realize, oh, I can just do an easy substitution here, or I can just, oh, at this point, it just, the power rule, right? Eventually you'll reach a point and say where, hey, I can just multiply across and that integral is not going to be bad. So you'll stop the table with when you hit one of these three situations. Let's actually do some examples. Let's do the one I asked you to look at last time, x to the fifth, e to the x. Now, of course, we appreciate that this is going to be kind of annoying to do integration by parts directly. So instead, let's set up a table. So differentiate this, get 5x to the fourth. Differentiate that, get 20x cubed. Differentiate that, I would get 60x squared. Differentiate that, I would get 120x. Differentiate that, I would get 120. Differentiate that, I would get 0. Stop! How do you write that? Once you hit 0, this is one of the situations where you know to stop. Now, what you can do is you can keep integrating this guy, right? So here I kept differentiating. Here I'm going to keep integrating until I hit this line. Integral of e to the x, well, that's easy. That's always just going to be e to the x. So here's how it's going to work out. I'm going to multiply this by that and take a positive sign. Multiply this by that, take a negative sign. Multiply this by that, take a positive sign. This by that, take a negative sign. This by that, take a positive sign. This by that, take a negative sign. And that will take a positive sign. So the result of this is going to be x to the fifth, e to the x, minus the negative sign, 5x to the fourth, e to the x, plus 20x cubed, e to the x, minus 60x squared, e to the x, plus 120x, e to the x, minus 120 e to the x. Then we're going to have plus the integral of 0, which we know is just a constant. So we end up with that guy just being, this guy ends up being your plus c. Now, if you're interested, you can do this directly with the formula. And eventually you get there. It probably won't be a lot of fun, but you can try if you want. Doing integration by parts 5 times in a row will actually get you this. So if I call you this guy I, then here I'd be able to say I is equal to, well, it's e to the x is a common term. So it's just x to the fifth minus 5x to the fourth plus 20x cubed minus 60x squared plus 120x minus 120 plus c. So doing it with a table actually makes it a lot easier to keep everything in line. Because if you were to write this out and do like 5 integration by parts and put parentheses inside of parentheses inside of parentheses, it's not going to be fun. You'll probably make a mistake. But with a table, it's not so bad. Any questions on how to do this table? Let's do the other situation. How would you deal with a revolving situation? Let's redo that example. So you recognize I should be doing integration by parts. You also realize that derivative of e to the x is e to the x, and if you differentiate cosine of x twice, you get back to cosine of x, well, negative cosine of x. So you kind of understand that this isn't a straightforward one. So what you would do is you start, who did we differentiate? The cosine. It actually doesn't matter here, but put the cosine x first, just to obey Leate. Keep integrating that, that'll give us e to the x. Differentiating this, minus sine x. Differentiate that, we'll get minus cosine x. What you notice at this point is that this is that, right? Of course, there's a sign change, but that doesn't matter. Signs can always be factored out. So I would stop the table after 2 iterations. Right? I get to a point where, looking across, I see the original. And so, now, this times this with a positive sign, this times this with a negative sign, this times that with a positive sign. And so what this would look like is e to the x times cosine x positive, minus sine x times e to the x, but the negative, so the negatives would cancel each other here. Plus the integral of negative cosine. Which again, at this point, you realize that that is the original, and you just do algebra move to the other side. So add I to both sides, you get 2i, then you divide by 2. And get that answer. You can look at a situation where neither of these options happen, where you don't get 0 and you don't get the original back. But you know you can stop when you see something easy happening. So let's actually redo a previous example. So you can compare tabular integration with integration by parts. They're the same method, it's just that the tabular method is sort of an algorithmic way of doing integration by parts, where you don't have to worry about plugging in the formula. I think we did one that looked like x squared ln x. Now for this one, our u, according to Leate, would be the logarithm. So let me write this in the other order. Derivative of ln x is 1 over x. Right? Now, one thing you can start to appreciate here is that this will never actually hit 0. Right? Because this is x to the minus 1, you're going to differentiate, get an x to the minus 2, then x to the minus 3, then x to the minus 4. It'll never actually hit 0. You'll just get 1 over x with increasing powers. So you know that that's not going to terminate at 0. You also realize that you'll never get that ln back. Right? Once you get to here, it's power rule all the way. Right? So that ln is never going to return. So you're not in either one of the original situations. However, now when I find the derivative, the antiderivative of this, that's x cubed over 3. But it turns out I can see that if I were to multiply across, that actually gives me something pretty easy. That's just x squared. That I can do with the power rule. So I really just do one iteration of this guy. And I immediately stop because I see that if I multiply it across, I actually get something pretty easy. So even if you only have to do integration by parts one time, the tabular integration is going to pick that up on the first iteration. Right? So you know there's a plus sign here, it takes a minus sign here. So this guy is going to be this times that minus the integral this times that. minus third x squared dx. And as we got last time, this just becomes x cubed over 9 plus c. Right? So that's called tabular integration. And applied it in several situations. There are some people who completely replace integration by parts as it's known with this technique, and that's of course fine. It's up to you, it's up to your preference. Normally I do a combination of both. If it only takes one step, I just do it the way I showed you last time. But if I'm doing something that is revolving, or it takes a bunch of steps like x to the 5th, e to the x, I definitely just do tabular. Questions? So that pretty much wraps up what I wanted to cover. So we'll just finish off with a medley. How about you try these? Or I'd say let's try them together. So here's A. Here's B. Probably what I want you to do is I'll give you 5 minutes, and then we'll run through all of them. But at least run through all of them and just do the first step. Just figure out the approach you would take. Okay, I'd start this problem by choosing this to be U, that to be dV. Right, so you can go through all of these and just get that first step down. Let me see where your intuition is, and then if it pans out, we'll actually complete the problem together. Okay, let's see. A, what would you do? What was your first step? Ideas?
I just use substitution.
Just use substitution. Regular substitution. This is a trick question. It's not integration by parts at all. U equals x cubed. D equals 3x squared dx. So our dx would be du over 3x squared. And so when you plug it into the integral, you get 1/3 e to the u du. So that just gives you 1/3 e to the x cubed. Never forget, you always think of the simplest thing first. So that was just a regular substitution. B. We know the derivative of tan inverse. That's 1 over 1 plus x squared. But we don't know the integral yet. I also believe this was a bonus on the review. Well, what would you do here? What was the first step? Well, first step? What do you think?
Would you do substitution for this one also?
What would you substitute?
How do you put u as, or no, it's integration by parts, but,
Okay.
so you do u as tan, inverse tangent, x, and your dv would be dx.
Alright, so this was a trick where you just think of 1 dx as the other function. Okay, so the derivative we actually know. I just told you that's 1 over 1 plus x squared. The integral of that would be x. So I'm going to call this I. That means that I is equal to u times v minus the integral of v du. How do you integrate this?
Don't you do a second substitution?
Now you do substitution, right? U equals 1 plus x squared. Your du would be 2x dx. You divide out that 2. Ultimately, you'll do a substitution, and the answer you'll end up with is 1/2 ln plus c. So at this point, just do a regular U substitution. U equals 1 plus x squared. Details left doesn't read it, but you'll eventually get an ln out of it. Because you'll end up with 1 over u times that half. Now this one seems surprisingly similar to the first one, but it does have some significant differences. Because notice now, the polynomial that's in the that's multiplying the exponential actually has a higher power than this guy. So that seems to suggest that substitution alone isn't going to be enough, but it's probably how I would start anyway, because e to the x squared is complicated. However, how would you actually start this? Well, you think of it how, kind of mentioned this idea before, is to actually, when we were doing something like x cubed divided by the radical of 1 plus x squared, we realized that we could think of the x cubed as the x squared times x. And so that's what I would do here. Okay. So now I can do a U-substitution here. That's going to take care of my du. This x squared that's left over, well, that's going to be the u. So I can do a, well, don't want to get the u's mixed up. So let's do a t substitution. T equals x squared. So this means that your dt would be 2x dx. And so your dx would be dt over 2x. So now when we plug this in, we have x squared times x e to the t. Our dx becomes dt over 2x. This x will cancel that one. This x squared is actually t. So we end up with that integral. And now that's one that starts out with a substitution and ends up in an integration by parts. So sometimes you have, again, multiple methods that you'd want to try, that you need to go through to get to the answer. And you don't always go in a particular order. So we've done ones where we started out integration by parts, ended up with a substitution. This is the opposite. We started out with a substitution, but now we clearly end up with a situation where the integration by parts would take effect. And so you end up with the u equals the t, and the dv equals the e to the t dt. And then you continue with integration by parts, and we actually know what that would look like. So that was t e to the t minus e to the t when we did it. And so that ends up being, now we just replace it. T is x squared. So ultimately that ends up being x cubed e to the x squared dx. Another interesting example there. E to the radical x is interesting in a similar way. Can I erase this? Yeah.
What did you do to the, like the dt over 2x? What happened to the 2?
I forgot it. It should be factored out as a constant. Trying to see if you're paying attention. Good job. Can you get rid of this? E raised to the radical x. Now I told you before that e to the x squared has no antiderivative, and so you might wonder, would e to the radical x have one? Seems a little bit more complicated, but it's actually not. This one actually does have an antiderivative that we can write down in terms of the function that we've seen before. Now, there are a couple ways you can deal with this one. But starting out with a substitution would be the way to go. So you set u equals x squared radical x. I set t equals radical x. Your dt would be 1 over 2 radical x dx. And so what you end up with is your dx ends up being 2 radical x dt. Now, as I said, there are many ways to think of the next step. So you start out this way, and then you kind of run into a hiccup. You get into a situation where, okay, for substitution to work, the derivative needs to be somewhere else in the function, and there is no radical x somewhere else in the function. There are times when you can kind of sneak it in, though, right? We can do that thing where we multiply and divide by something, right? So if you want to get a substitution to work and it doesn't seem to work, one way to force it is to literally force it in there the way you normally do, by multiplying and dividing. Another option is to actually just realize that your radical x was t. So you could actually just replace this with 2t dt, and that would also fix the situation. Another way you can look at it is from here, you could square both sides and then differentiate both sides, and you'd eventually get here again, right? So there are lots of ways to actually do this. A little bit more sophisticated than a substitution we've normally been doing so far. Like I said, integration is very complicated compared to derivatives. So there are a lot of techniques and a lot of mixing and matching that's going to happen. But that's what Calc 2 is about. You'll have a lot of fun with integrals in Calc 2. So at this point, I can actually start replacing everything. So here I have e to the t, because that's my radical. My dx is now 2t dt. Ultimately, I get 2 times the integral of t e to the t. This is integration by parts. U equals t, your dv equals e to the t. Eventually, we'll get t e to the t minus e to the t plus c. So this is 2 times radical x e to the radical x minus e to the radical x. And that's the integral of this one. I mean, it looks very similar, but this is probably one of the more complicated integrals that you'll see in this class, because conceptually there's a lot going on. Even though writing it down doesn't seem like a lot, to actually see that this is what you had to do is actually pretty challenging for the average Calc 1 student. So it doesn't really get harder than that for integration with Calc 1. But we're kind of finished. We're finished with the syllabus. Integration by parts was the last thing. Remember, we have a test on Wednesday. Hopefully you work through the solutions on your own and you're pretty solid with them. So I'll post the answers later today, this afternoon, this evening. And on Wednesday, I guess we'll just do something else. Do something for fun. All right, we'll stop there. I'll see you guys on Wednesday.
Well,
Tomorrow.
A separate review for the final?